family of distributions after reading the chapter. How many of you were familiar somewhat with the concept of generalized linear models before an exponential family? So like 3 or 4 of you, right? I only saw 3 hands up. Okay, yeah, it is not always something which is covered in sort of basic statistics courses, but it was in 80s or 90s, I think late 80s or early 90s, when this thing was being established. It was a big deal, because what it did, it put under one umbrella a lot of models, and then the software could have been developed to, which had the same look, same interface, same inferential tools like p-values and composite walls for all kinds of regressions. It's general Gaussian, that your typical least squares regression with Gauss-Markov assumption, Gaussian regression falls under that umbrella. And then logistic regression, which how many of you have done or know about logistic regression from before? So logistic regression is part of it's a big part, it's like a very substantial part. Well, in the sense that it's been used before, but there was always specialized software for logistic regression. Then there was specialized software for log linear models, Poisson regression. And people would build like other things. So what McCulloch and Elder and then Peter Green and others, what they have done is, first of all, they established a common framework with one big formula, messy and kind of ugly, but still. And then, the stuff that you can derive from this formula, which applies to all those models. And with lots of customization, you can have this link, you can have that link. Like probative regression was also a thing before generalized linear models, and suddenly this is all part of generalized linear family with just non-canonical link, it's called. So, and then, p-values, confidence intervals, they all kind of fall from the same. So it's basically the same general software. In fact, there was a software before S and R were precursor of S was R. Before that, there were a thing. There was actually a GLM software. It was built in Fortran and it was distributed for free by I can't remember whom. So you had to prepare data in a specific format, and you start the software, and you could it was a bit interactive, specifically for generalized linear models, because it was already a big thing. So it is important, and it is kind of usually covered in categorical data analysis, because those are the kind of things that first fall into the generalized linear models. Analyzing discrete kind of data or these discrete responses, because now we will see that we don't have to have a discrete categorical predictors, X's, right? With tables, everything has to be categorical, because somehow we have to categorize it into cells. Now this can be extended where the responses are not categorical, where the X's are not categorical. But when you have a categorical outcome, like binomial, multinomial, or counts, then you can just use simple linear regression. Well, you can, but it's not efficient, and it doesn't quite work. So you have to go to specialized models, and all those specialized models end up being in an exponential family of models, and therefore generalized linear model family. So it was a big deal. Okay. So intro to GLM. This is the kind of thing. I don't know why this is the other way. So they all start with this rather, send to the projector. Okay, I'll send it. I have to wait. Oh, hello. Okay. So it all starts with this rather ugly format for all kinds of distribution, density functions. Now you look at it and you say, I don't know any density functions looks like this, but since you read the chapter, they all fall into that. You just have to massage the thing. So you're going to ask me, what do I have to remember for the quiz or for a test? You don't have to remember this formula or even the so-called simplified formula that Agresti has. But what's going to be important to remember that as part of this formula, you have exponential to y times something, parameter, something which depends on the parameter or is a parameter itself, because that gives you a so-called canonical length. Everything else is a fluff. So this gives you density in terms of two parameters. Can you name me a density which has two parameters? Anybody? A known density function which has two parameters, known distribution which has two parameters. I need to understand that I need to know that you understand what a parameter is. So give me one example of a density which has two parameters.
Normal?
Yeah, a Gaussian distribution, so-called normal distribution. That's true. So what are the parameters, typical parameters of a Gaussian distribution? Mean and variance. Now, of course, you could rewrite the Gaussian distribution using other formulations, but they will all also have something, two parameters. It's just that it might be functions or something, right? So parameterization means rewriting things, and the fact that we chose mean and variance for Gaussian to write it in this specific format makes a lot of sense, because those are first two moments, which are important, and they kind of describe the density nicely. But it doesn't have to be like this. If you ever saw gamma distribution, there's at least two common ways of writing gamma distribution. It's the alpha and beta, alpha and gamma. So one of them is, and then the mean is either a multiplication or division of each other. So you can write the same thing in various ways, depending how you kind of structure things. So this is the whole point here. You can write a lot of density functions by massaging algebraically things, which has two parameters, and end up looking like this, even though it's kind of an ugly format. You can write it, so we'll see, but we saw in the book, you can write a normal distribution, something like this, and gamma distribution, and binomial distribution, and Poisson. Now, binomial and Poisson and negative binomial, they all have one parameter, because n is not a considered parameter in binomial or multinomial. So n is basically something which is given, it's not a parameter. We don't estimate n. But they all have one parameter, which is a mean of some sort, right? Because probability for binomial is the same thing as mean. If you take a binomial and you take e of x divided by n, you get pi, because probability of a Bernoulli, expected value of Bernoulli is the same as probability of getting 1, right? Of course, that if you decide that x is, that y is either 1 or 0. So in some sense it's mean, but the probability, that's one parameter. In Poisson you have a mu, which is the rate, and in multinomial you're gonna have, of course, p, but for every, so it gets it's a little bit different. So multinomial is a little bit different. We won't be doing multinomial, at least not now, for this. But gamma has two parameters, and of course normal has two parameters. So this, you can write distribution which has at most two parameters. Of course, not every two-parameter distribution can be written like this, but all the nice ones, well, all the ones that we know and love, can. So here it is. So it's basically this theta is going to be one parameter, and this psi is potentially in the other parameter. For distribution which only have one parameter, the psi will not be anything, right? It will basically as part of some numbers or some. It will not appear when you write binomial or Poisson in this format, but for normal, it will. It's just that when you write it in this format, your typical parameter in your typical specifications of your distribution, say for example Gaussian, this theta is not going to be exactly mu, but it will be one of the parameters or a function of one of the parameters, and it will end up being a function of mu. For normal, actually, it is. And a psi is sigma squared. So for normal kind of works exactly, you just mess around, but for others, as you will see, not work. So what's important is that you remember that if things are written in the exponential family format, then there is exponential to y, which is the should be yi, and this should be, everything should be I. I'll come back to this. So there is exponential of the of the main variable of a density, x, y, whatever you call it, times one of the parameters which could be a function of your original parameterization, but it's just containing one parameter. So the theta might be the original parameter, or it could be some functions of the original parameter, but of just this one parameter. So this theta only depends on one of the parameters, which will always be parameter related, almost always, I forgot how this for gamma, always be related to parameters which relate to the mean function, at least for the densities we know. This will be related to the parameter which compose mean function, which is of course, for Poisson binomial, that's the only parameter we have, is something related to the mean function, because we don't have psi. Okay, so that confusion, I'm hoping, basically you can, like I said, you can write any equation with some parameters which are unknown quantities, but you can write it the other way where those parameters are expressed differently, with like a squared, or as you see, log os, or something. Now, this psi is typically called a dispersion parameter, first of all, because it ends up being sigma squared for Gaussian. So, yeah. But also, when we start doing score functions and the information, Fisher information, and looking what is in terms of this, what's a mean and what's a variance. This psi parameter is kind of like a scale in general. For Gaussian, it's exactly sigma squared, but for, I guess, if I could remember gamma parameterization, this might end up being, something which is related to the scale of dispersion around the mean. So that's why it's called. For most of the stuff we're going to be focusing here, which is Poisson and binomial, the dispersion parameter is not there. It's assumed to be 1, as you see in the software, because it's sort of hiding in between other expressions, but there is no extra parameter to estimate. Okay. Yeah, that's what I just said there. Now, so I guess he has I think, somewhat confusingly to me at least, it's always been a little bit confusing to me, but it is what it is. He rewrites this using this format if you assume that psi is not a parameter, like that there is only one parameter in the function. You can kind of mangle with this and rewrite it like this. So basically, this is going to be e to y theta divided by a psi, but a psi it's known, times e to the b theta divided by a psi, right? Minus e theta, because we can expand this exponential, times e to the c something, right? So the first thing is e to the y theta divided by a psi, which is assumed known, so it's some kind of a function of theta. So that theta tilde might not be exactly the same thing as that's why I find it a little bit confusing. But the main thing is there is y and something related to the first, some function related only, depending only on the first parameter. So there's a product between the argument of the function, of the density, y or x, whatever, times a function which will be related to this one parameter, but it only depends on this one parameter. And theta, theta nu, or mu, those are just different names, and it depends how you write things up. So this is important, this y times something about parameter, y times something about parameters, because this theta will be a parameter in this formulation, and this q of theta will be parameter in that formulation, but we keep thinking about parameters as we learn the densities. For binomial, we keep thinking about pi as a parameter. For Gaussian, we keep thinking about mu. For Poisson, we keep thinking about mu. So this theta is going to be some kind of a function of this one parameter. So once you see this, that's kind of everything you need to know, because that's what identifies the canonical. The other things which I find a little bit not cool with that is that from that formulation you can get score and information matrix and means and variances by looking at B. You cannot get it from there, you have to kind of work your way around it. So, but again, for your information, what's important is that once you can, if you can write the density in whatever e to the y parameter, I mean not the parameter, e to the argument of a function times something related to the one parameter that you have for single, either this way or this way, then what's here and what's here is important, and everything else is outside of exponential. There could be other exponentials here, but they do not depend on well, they can, but they don't depend on the product of y and theta. Yeah, this is also kind of nice because it says, okay, this y, something related to y and theta, so this is something related to the parameter, minus some function of a parameter. So this kind of gives you like y minus mu kind of thing. And this is divided by variance. So of course it's not like this, but it has this interesting format. Anyways, for your information, is what is important, once you write the density in a way that has this term, then this thing, y times something related to the parameter, then this thing is important because this identifies the what we're gonna see is called a canonical. Okay, yeah. So this is, and Agresti does it. This is, except that he doesn't switch to tilde notation. He uses the same letters as the original long form formulation, and it gets confusing. He says a is equal to a something divided by something. Well, how can it be? Those are different a's, different b functions, and different thetas, and I think different size, although I'm not quite sure. So again, for what's important is this term or this term. Once you have this, then that's important. Okay. Now, what we talked about so far is the exponential family of distributions. So Gaussian distribution is a family of distribution because with two parameters. Exponential family of distribution is even larger family of distribution because you have one or two parameters, but you have different formulations of this, and it includes all kinds of distributions like binomial, Poisson, and all that, right? And Gaussian. The next step is how we're going to use it to do modeling, to do data fitting. So in data fitting, remember we have a response, and we usually have one or more predictors. That's what we model. If you want to have a regression of some sort, then you have a response and one or more predictors. So you have x's, which are predictors, and then you have response, which is y. And response can be anything that is suitable for one of the exponential family of distributions. So of course for Gaussian this could be a numerical thing, but for Poisson it's going to be a count, and for binomial it's going to be number of successes, as it were, right? So so this is a response, and then there is a bunch of predictors, which we try to relate the predictors, the x's, to the response, at least to the mean of response, right? Average of response. So all the regressions, all we've done with contingency tables so far was of the same flavor, except that we focused on specific question. Well, we focused on estimating parameters, like maximum likelihood estimated of pi and mu, but then we focus on the parameters of association, which gives us the strength of the relation between x and y. So we're gonna go forward, and instead of sort of looking at 2x2 tables, I mean the two-dimensional tables, we can now go further and look at association between not just one x categorical, but many x's and the y. With tables, we had, so if it's a binomial table, we're looking at association like risk ratio or odds ratio, which is basically a function of two pi's, right? We have two binomial distribution, two pi's, and then we take the function of those two pi's and look how does x explain y. X being the rows in the matrix, y being the columns. How does x explain y? So how does aspirin explain or not, or treatment explain the disease outcome? But now we're gonna make it much more explicit. Y is a response, like in all your regression problems before. Linear regression, reversal regression, and whatever else you studied. Y is a response, and then there is one or more predictors, x's. So y is the random component, and we're trying to, and it has a distribution. It's a stochastic or random component, a stochastic component, right? It has a distribution, and the assumption about this distribution is what's going to drive the choice of which of the distributions from the exponential family we will choose for modeling it. So that's y. But then we have a systematic component, and that's almost a definition of general linear models, right? You basically say, okay, the distribution of y is going to be one of the exponential family distributions with one or two parameters, but one of the parameters typically is something related to the mean, which is going to be re-expressed in theta, so that one parameter of this distribution, we're going to take some function of it, and it's called a link function, take some function of the mean, and related to the predictors as a linear combination. So we are trying to, this is the parameter, the kind of the important parameter, there's two parameters. This is the important parameter of y, of distribution of y. In most cases, that's the only parameter of distribution of y. We can call it mu, expected value, but we can call it anything. That mu will be expressed in different ways in the exponential family, and it will be hiding inside theta. So theta is going to be probably a function of this mu, or it might be mu itself. And we're going to say, okay, some function of mu, this some function has to be a monotonic function, meaning it can be invariant. So it's always rising. There's no flat spots and there is no like up and down. So this monotonic function is the rising or falling of mu has to be, we express it. We choose this function and we express it as a linear combinations of predictors. So that's how we join the explanatory variables with the response using distribution. So this is called a link function. Now, we will see how this can be relaxed. First of all, it can be easily relaxed by adding cross products, like maybe interaction terms. So it doesn't have to be exactly linear combination. We can start relaxing this. And later we'll see how we can relax it. So it's not only linear functions, but any smooth functions using generalized additive models. But for now, and this eta, this letter is almost always used to denote this linear predictor, or this kind of linear predictor, and is the function of the parameter of the distribution, the link function, which we assume is equal to this predictor. Now, one thing I didn't say before, although you've probably seen it, typically when we have problem for generalized linear modeling, we think of it as line by line, observation by observation. Like in tables, when we put tables together, those observations are kind of clumped together, because really there's only so many choices of x's and y's. If you have a 2x2 table, there can be at most two choices for y and at most 2 choices for x, so there's at most 4 choices for any observation. So we don't have to write a line by line. This person, aspirin or treatment like this, and the response like this. This person, treatment like this. This is, in a table we collapse all together because otherwise there is nothing else to distinguish the observation. It's just those two variables, outcome and the predictor. But for generalized linear models, we start to think like we are used to linear regression. Each line in the data is the unit of observation. So we're gonna have for each unit of observation is going to have a response, whatever it is, success, or success. I mean 1 or 0 essentially. For Poisson, this might be counts, because now we're going to count things for the specific unit of observation. If we're counting every time we, for different streets, counting number of bicycles or cars passing by at the distance of different streets, then each street will be a unit of observations. So unit of observation is important to understand what is a unit of observation. Those units get collapsed in the table, but here we write them line by line. So y is going to be response either the count for Poisson distribution for particular unit of observation, or failure success for the binomial distribution. And so each line will have its own observation. So therefore, each of those parameters, and that's why it should be I here, it possibly can be different for each line of observation, because we usually know psi. Usually we assume psi, well, for linear regression, we assume everything has the same variance added. It's called homoscedasticity. But the mu will depend, because we're trying to relate the expected value of some sort. We're trying to relate it to the predictors. So of course, each line has different predictors. Therefore, there should be theta I here, because the mean, or whatever the parameter of distribution, will be dependent on predictors. Therefore, it's going to be different for different I. So the format of the theta is going to be the same, like the function of mu or whatever, but the actual value will depend on x's through the linear predictor, right? So the actual value of mu I of theta I will depend on predictors. Of course, it's going to be different for different i's. So, general format is the same, but things will differ. Different y here and different theta or mu here, because it's related to x-i's. Okay. So, and this is where sometimes it gets confusing. There is this thing called canonical parameter. Or canonical, the word suggests it's important. It's a canon. And the canonical parameter in the generalized family of models, Agresti talks about this Q of theta I canonical parameter, but it's whatever multiplies y, which is a function of the underlying parameter of the distribution. That function of the underlying parameter is the canonical link or canonical parameter. This itself is called canonical parameter. Once we massage your distribution to look like this, whether there is e to y theta, meaning e to y times something that depends on the parameter only. I think nothing else matters anymore, and that's something that depends on the parameter, which will depend on mu or pi or whatever. That thing is called canonical parameter, and the function of our usual parameterization of distribution, that function is called canonical link. So let me, so this is basically expressed this. Canonical parameter is this theta I, once we express things correctly, or Q of theta, or aggressive formulation Q of some other theta. The canonical link is that function, is the theta expressed as our usual parameter of that we're interested in and we're interested in estimating. Questions? We'll see the examples soon, but questions. You have a question?
Yeah, so how's there a relationship between what we're doing with GLMs versus what we did with two-way tables in the last two lectures?
Yeah, so we'll get there, but I already mentioned this. So we did two-dimensional tables. Let's take the simplest example, 2x2 tables, and let's take rows being, say, treatment or exposure, as Piotr called it, and columns being outcome. So there's two potential outcomes, dead or alive, or recovered, not recovered, or got a heart attack, did not get heart attack, and there is two potential exposures or two potential treatments, like placebo, aspirin, as we'll see in a minute. So X, so for each unit of observation, those are people, I assume, taking aspirin or placebo and having heart attack or not. Each person is going to be one unit of observation. And for each person, we're going to have two numbers, two things. One of them is going to be outcome, and the other one is going to be treatment. So you can think of the data as being, well, usually put X first, treatment, and it's going to be 0 for placebo and 1, it's a categorical thing. And then there's going to be outcome. Yes, heart attack, no heart attack. So you have X's and Y's. Now, the way we looked back at this, because things were simple, we just lumped it all together in one table with 4 cells. Because each of the unit of observation belongs to one of the 4 potential possibilities. Right? You either had or not had a heart attack, you either took or didn't take aspirin, right? So it's 2x2 form. And analyze it by saying, well, what's the question of interest? One question of interest is probability of heart attack dependent on taking aspirin or not? So you have probability of taking heart attack with aspirin, probability of having heart attack with no aspirin. If the data was longitudinal prospective, then we can estimate those probabilities and divide them and basically see whether the risk ratio is 0 or 1. So this is doing the same thing. Now we just think of this rows as being one of the potential X's. Except that now we might have two aspirin not, female or male, age, which is not possible to write in a table format. I mean, you can put 3-dimensional table for sex, like binary sex, male, female, and real or not, or you can put a series like 2x2 times 2x2 tables. But once you put age, which is a number, then you cannot really write in terms of tables. And what if I add a bunch of other things? Has this genetic mutation or not? And and suddenly the table concept just collapses. We cannot write in tables anymore. But the idea is the same. If you have a single predictor, or maybe two predictors, they're all categorical, you can put it in tables, or you can write it line by line and assume this. And in tables, we assume, in a 2x2 tables, we typically assume binomial distribution of y given x. This also, you can put binomial distribution here. So I'm just going to binomial distribution, that the probability depends on x. And we'll see that it depends on x in exactly the same fashion as we saw in the tables, at least for the odds ratio kind of analysis, which is not risk ratio. Okay. So this is a simple example just to, using Gaussian, we don't need Gaussian for the categorical data analysis, but this is the one everybody knows, and I guess it goes for this. So Gaussian, and it sounds more general. It's two parameters, although the fact is we usually focus on estimating one parameter. So you only make one parameter in Gaussian distribution as being a function of predictors, right? And only mu. We say the mu is equal to sum of xij's times beta j's. That's what we do in linear regression. And the other parameters kind of estimated later. So even though it's two parameters, we don't really worry about the second parameter. We assume it's the same and estimate it later. But this is the original format of the Gaussian distribution that you know by heart every time you get up or are woken up in the middle of the night. E to minus y minus mean squared divided by 2 sigma, and with this little thing which makes it integrate to 1. This depends on sigma squared 2 or sigma. And if you spend enough time on this, you can rewrite it like this. It's just doing high school algebra kind of stuff. So you write it like this, and suddenly we see that this looks exactly. We stare at it, and we stare at our long form, our original Gaussian, our original. Remember the original formulation of the exponential family. There's y times something about the parameter. Here is just original parameter, so this is great. This could be a function of the parameter. Minus something related to the parameter, plus something or minus something, it doesn't matter. Well, it was actually minus there, so we read it as minus. But this only depends on the parameter. In this case, it's a function of the parameter again. In this case, it's mu squared divided this, plus something which depends on the y, and something which depends on the other parameter, and divided. Oh, I see this one is also. Oh, this has to be divided. I forgot. This is also, you allowed in the long form. You allowed to divide it. Go at home and stare at this because I don't want to be flipping. So here you're allowed to divide it by something which is related to the second parameter, right? In this formulation, and then you have an overall function of y and the parameter. So. What's going on here? This cable is not working very well. So, if you take this and write down your long form, you will see that this conforms to the long form. This is the C of y psi. Psi here is something which depends on sigma squared. And this is the y times theta, where theta is something which depends only on the first parameter. In fact, it becomes exactly this first parameter. And this is minus something which is a function only of the first parameter. In this case, mu squared divided by 2, and divided by something which only depends on the second parameter, which should be divided. Of course, it wouldn't matter. I mean, you can always multiply by inverse. But in fact, this is divided by sigma squared. So it's this extra function a of psi, which depends only on the second parameter. So the only thing is, does it have the same format? Does things depend, those funny functions a, b, and psi, do they depend only on the things that they're supposed to depend on? And the answer is yes. But like I said, this is the most important part, and we immediately see that the canonical parameter is the actual parameter we love about Gaussian distribution, which is mu. So the canonical parameter is exactly the same as our typical parameter. It didn't have to be, because once we write things, it could be like some mangling of things. So that's the important part. So the canonical parameter is in fact mu, the original parameter, and therefore canonical link is going to be nothing, identity link. Going from theta to mu means just write it down. Okay. And then the book is doing this through actually I will have some slides from Professor Canis through binomial and Poisson, except that they write it in their own, quote unquote simplifying notation, but same idea, and this gives you the sort of idea how what's going on, and then the parameter. The things multiplying here will not be exactly the original parameters, the original mu, it will be some function of mu. That's what makes it interesting. So in Gaussian, the link is itself, it's an identity link. The function of original parameter that we're interested in estimating mu, is going to be mu itself. Therefore, we're going to make mu related to the linear combination of x's and y's. That's the so for Gaussian, we don't have to do any simple linear models, general linear models, only because we call it, but it's nothing needs to be done. For Poisson, once you write down Poisson in this way, you will see that that you have a y times log of mu once you write Poisson, and therefore the link is log of mu. And look at that. For binomials, there's a simple distribution. Once you write it, becomes a bit of a mess. You will see that there's this y times log of pi divided 1 minus pi, or pi I divided 1 minus pi I. So that becomes a canonical parameter, and this function becomes a canonical link. Meaning that's the simplest. Canonical links are not really preferred links, because you can take any link as long you can make this g as anything as long as it's a monotonic function. But they kind of pop out from the formulation, and they call canonical. There was nothing really special about them, except that people use them most of the time. But this is convenient. Once we write things in the proper format, exponential family format, the binomial, the parameter itself becomes the odds ratio, right? I mean odds, no, this is just log odds. So log, okay, we don't care much about logs, although when we did estimation in 2x2 tables, we did log odds because things just are better behaved when you take log of ratios, because you take say, log of something minus log of the other thing. As long as things are not 0 or 1, then things behave better than the ratio. So we can think of it, well, maybe this is what I want to estimate. Or maybe I don't really care about pi, I might care about odds ratio. So this might be okay. Maybe I should always think of binomial distribution in terms of odds ratios, or odds, and then odds, not odds ratios, log odds. But that's what pop out there out of when we write. So I'm just gonna flip through this. This is straight from the book. This Professor Canis slides. That's the formulation where we saw this already. But again, the important part is going to be this. And then and that B is not the same B that is in the general formulation. So once I give you formulas for score function and the mean and variance, which is going to depend on B, is on a different B. It's the B which pops out in the original formulation, because this is more like E to B something. So that's the confusion. Although the fact is it doesn't go into it is not here into inference to give. And then we say, okay, we're gonna relate our original parameter, the one we're interested in, usually mu, to be a linear function. So the function of the original parameter we're gonna relate it to x's through this. And of course, this G could be either the canonical link, or it can be any other link. But there are some classical links. I mean, the logistic regression has really two links, probit and logit. And canonical link is this, right? Basically, if you take whatever Q of theta, if you take whatever is multiplied by y in terms of the parameter, that is called canonical link. And in this case, it's going to be log of cos. So there's Poisson. If you write it blah 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 in this ugly format, then you have e to y log mu. So that thing you will also see in the long form format. You said there's going to be minus something plus something, but e to y log mu, that's the important part. So log mu is this canonical link in this formulation. And in fact, for Poisson, it's rarely that you use anything else but the canonical link. Sometimes people use log. To stop life instead, but it's usually canonical. And then for binomial, once you rewrite things from here to this format, you have e to log, y log. That's why you see log, because there was no e here, so then you have e here, so you have to get something to log, so that e's disappear. But and y is just 0 and 1, so it just says yes or no. So e to log, there was no y. If y is equal to 1, there's e to log, which is basically this itself, right? But anyways, that's why it disappears. So it's e to log of this. So this is the canonical, or sort of the most used parameterization for doing logistic regression, right? That this is going to be related, log of pi over 1 minus pi is going to be related to the sum of xi and beta j's, xij beta j's. But it doesn't have to. Now, okay, any questions? I need a sip of water, so I need to take a break now. Okay, so let's have a few minutes break, 5-minute break, and then we'll finish this, then we have another break, and I'll do a little R. Okay, so 5 minutes.